All right, let's try to solve Module 5. It should say number 3. Let's read the problem. It says, the figure below shows a region of space with an electric field. And remember, the electric field, we can describe that in two different mathematical ways, right? Using something called the E field, or using this new thing that we learned called the V field. So here it says vertical lines indicate equipotential surfaces. So here we are given a picture of the V field. A particle with charge minus 3 nanocoulombs is initially at the location of the minus 20 volt equipotential line. So that's already drawn for us. There's a negative charge at the minus 20 volts. So be careful about this minus. Sometimes a little hard to see because of the dashes. At time t equals to 0, the particle is released from rest. Ignore the force exerted by the Earth on the particle. The first thing says, draw E field lines on the sketch provided. So we know since the E field and the V field are both describing the same electric field, given one, we should be able to at least qualitatively figure out the other, and definitely quantitatively also. Okay, so let's see how we would work this. As a general thing, I noticed that in this region over here, the equipotential lines are parallel. In this region over here, the equipotential lines are parallel, but they're more spaced out. If you notice, all of them have a difference of 20 volts, right? 120, 100, 80, 60, 40, 20, 0, minus 20. And we know whenever the equipotential lines are evenly spaced out, that means it's a uniform electric field. It's a uniform E field if I draw them. So these two regions are going to have a uniform E field. And then something funky is going to happen in the middle. So let's see if we can work with this. Well, first things first, which direction does the E field point? Well, the V field values are going down in the left direction. So as you go to the left, as you go in the negative direction, see our scale is already set for us. So we already know that right side is positive x. And as you may have discovered this week, that the E field always points in the direction of decreasing values of potential. So in this case, generally the E field will point to the left. Let's try to make this shape though. So in this first region on the right side, it seems to be uniform and the equipotential lines are pretty close together. That means the potential is changing faster, and since the E field is proportional to negative the change in potential over change in x, that means it's a strong E field over there. How do I depict a strong E field? Well, I'm going to draw my lines close together. I'll put the arrows after I'm done with my diagram. I know it's to the left. So I'll put one over here. I'll put another one pretty close to it. I'll put another one pretty close to it. Yeah, they're decently close. Let's do it a little nicer. Right in the middle, close and close. But if we look at this left region, the V field equipotential lines are spaced out farther. That means the potential isn't changing as much for every change in x, which means the E field is weaker over here. And how do I denote a weaker E field? Well, I need to space out my E field lines. So let me space them out more. There you go. Compared to that first region, I can clearly tell my E field is weaker over here. Now the thing is, what do we do about that funky middle part? Well, another thing that we know is that the E field lines are always perpendicular to the V field lines. And since the V field lines are curved, these perpendiculars will also be at a slight angle. The middle stays the same. So see, hey, that's giving us a natural pathway to make those E field lines spread out. Now let me see if I can flex some of my sketching abilities. And something like that. Maybe not the most accurate, but there. The E field starts off strong on the right side, and now I can put my arrows in. The E field is pointing to the left. Oh, the bottom one looks a bit fuzzy. Let me try to clean that up. There you go. The E field starts off strong on the right-hand side, and then gets a bit weaker on the left-hand side, and there's a transition point somewhere in the middle, around the 6 to 9 centimeter range. Okay, I think that does it for one. Draw the E field lines on the sketch provided. Number 2 says, draw a qualitative velocity versus time graph for the motion of the particle until it reaches a potential of 120 volts, so until it reaches 12 centimeters on the scale. Okay, let's try to make sense of this. This is a negatively charged particle in an E field that's pointing to the left. Does it make sense that it's moving to the right? Well, remember that an E field is defined by what happens to a little positive test charge when it's placed in the field. So a positive test charge would go to the left, that's why the E field points to the left, and thus a negative test charge, like over here, will move to the right. Okay, great, so at least the question makes sense. Now what about the velocity versus time graph? I'm gonna start putting in a little bit of explanations of what I'm gonna do. I can label this as a weak uniform E field. I can label this part as a strong uniform E field. And I can label this part as a changing E field. Well, remember that the force exerted by the E field on a charge is given by the charge times the E field. Well, that means this leads to a weak force to the right exerted by field on the charge. And this one is a strong force to the right exerted by the field on our charge. And in the middle, we get an increasing force, right? On the left side is a weak force, on the right side is a strong force, and increasing force exerted by the field on the charge. Okay, well, we have to figure out what? The velocity versus time. Well, we're at force now. How can we eventually relate force to velocity? Well, we know that acceleration is proportional to the force exerted on a body divided by the mass of the body. Since the body, the object, is our charge, the mass stays the same, so I can basically say, let me write this, according, see, these are my explanations. I can make them in a different color. Put an explanation over here. The force that a field exerts on a charge is equal to the charge times E. So that's how I made these assessments about the force. My next thing I can do is the acceleration of Q is proportional to the force that the field exerts on Q. This is Newton's second law, right? Acceleration is proportional to force as long as mass stays constant. Well, that means I can now make these arguments. A small acceleration value. Here it's a larger acceleration. I can't write. Acceleration value. And, oh, what about the middle? Well, if it's an increasing force, well, it's an increasing acceleration, E-L-E-R-A-T-I-O-N value. Well, that middle one's a bit different, right? Everything we learned last semester on how to deal with accelerations, we always dealt with constant acceleration motion. So every now and then we stray out of that little niche and see some real world stuff where accelerations might be changing. Okay, well, that still doesn't directly help us with a velocity versus time graph, but it kind of also does, doesn't it? So I can do a velocity versus time graph. My charge initially is at rest, so at least I know where to start. I'll start over here. And it's always having a force on it that's exerted towards the right. So I can draw a force that the field exerts on the charge is always to the right, but that force is changing in value, leading to different accelerations. Well, remember how we depict acceleration in a velocity time graph. Acceleration is the slope, so I can say it's a small slope. Here I can say it's a larger slope in VT graph. And in the middle, it's an increasing slope. Aha! That gives us all that we need to draw our VT graph. I start at 0. In the beginning, it's a small force, and for a little while, it's that small force. So that'll cause my velocity to increase at a relatively small rate. Then, let's go a little bit farther. In the middle, my force is now increasing, which means I have an increasing slope. How do I draw an increasing slope? Well, I need to curve upwards for a little bit. And then I end with a constant larger slope as it ends up the last little bits of motion. So it'll be something like this, but it's a straight line. So this part is a straight line. This part is a straight line. This part is a curve. There. That took a little bit of explaining, but I think we got number 2. Draw a qualitative velocity versus time graph for the particle until it reaches that end part of the ruler. Number 3 says estimate the force exerted by the electric field on the particle when it passes the 0 volt equipotential line, so that's this, and when it passes the 80 volt equipotential line. So we want to figure out the force exerted on our particle when it's here and when it's here. That's another way of saying that. And then part 2 says determine the kinetic energy of the particle when it passes the 60 volt equipotential line. So that's right over there. show all your work and explain your thought processes. Okay, let's deal with the first one. Estimate the force exerted when it's crossing the 0-volt line. So this is part 3. We want to find force exerted by field on charge at the 0-volt mark. Therefore, we need to find the E field value, E field strength at that mark, because the force exerted by field on Q is given by Q times E. So if I get E, I can multiply it by Q and get the force. Well, how do I get the E field strength? Well, if you remember, the relationship between the E field and the V field is given by the E field is the negative delta V over delta X, or for anyone interested in the calc version, it's minus dV over dx, but you need to know the functional form of V to be able to take that derivative. We don't have the functional form here, so we're going to have to do some sort of manual method. Well, how much does the potential change over a certain distance? Put a minus sign with that and you have the E field. Well, if I'm looking at the 0-volt area, if I want to find the change around that area, I need to look around that area, right? And I do see my two values. See, at 0 centimeter, it was minus 20 volts. At 6-ish centimeter, it's 20 volts. I know it's not exactly 6, because exactly 6 is somewhere slightly behind, but you know what? We are estimating, and I just ruined my nice diagram. It says estimate the force, so I don't have to be incredibly accurate. If I need to be incredibly accurate, well, then I should have been given the function so I could take a derivative, but I haven't, so I'll work with what I have. I could say it's minus the potential at 6 centimeters minus the potential at 0 centimeters divided by 6 centimeter minus 0 centimeter. There you go. How much does the potential change over a certain value of distance? And the minus sign is there because the field always points in the decreasing direction of the V values. All right, we can do this. Minus at 6 centimeter, it used to be 20, it is 20 volts, and this is minus 20 volts. Volts. And 6 centimeter minus 0 centimeter, that gives me 0.06 meters. So, what do I get? I get a total value of 20 minus 20 is 40, so that's minus 40 volts over 0.06 meters, and I get some value that I need a calculator to do. 40 divided by 0.06. Oh, look at that. Special number. 667 volts per meter. Volts per meter is a perfectly fine unit to describe an E field with, but we also know that volts per meter is exactly the same as newtons per coulomb. Oh, don't forget the minus. Why did we get a minus over here? Does that make sense? Well, let's go look at our scale. Our scale says the right side is positive and Minus means the E field points to the left. Oh, hey, it makes sense. I will remember that for my evaluation. Then what? Then I need to estimate the force. So I've only found the E field. Well, now, if I want to do the force that the field exerts on Q, I can do Q times the strength of the E field, which was this, at, where did we find this? This was between our 0 centimeter mark and our 6 centimeter mark, so it's at our 3 centimeter mark. The field, the force that the field exerts on Q is given by, what was it, minus 3 nanocoulombs. Yep. Minus 3 nanocoulombs times minus 667 newtons per coulomb. So you got to do the 10 to the minus 9 for nano. So times 3 times 10 to the minus 9. The minus and the minus go away, which gives me a positive force of 2.0 times 10 to the minus 6 newtons. Well, that's a tiny amount of force. But hey, we did think about it and we knew that the force should be on the right, and we got a positive value for the force. Great. Okay, what about, so same method. And where was the second time we need to do this? We need to do this at the 80 volt, which is at the 10 centimeter mark. Same method at 10 centimeter mark. So what was my method? My method was the E field is given by minus delta V over delta X. I can do minus V at somewhere bigger than 10. So I'll check it at 11 and I'll subtract the 9 1. So that's 100 volts and 60 volts. So V at 11 centimeter minus V at 9 centimeters divided by 11 centimeter minus 9 centimeter. Well, what do I get? I keep forgetting my values. 100 minus 60. So I get minus 100 volts minus 60 volts divided by 2 centimeters. So I get minus 40 volts divided by 0.02 meters, and that gives me 40 divided by 0.02, which is negative 2,000 volts per meter, or negative 2,000 newtons per coulomb, and that's my E field at 10 centimeter. Okay, let's take a sanity check. 2,000, clearly bigger than our older answer of 667 in magnitude. Did we expect it to be? Yes, our drawing shows the E field lines close together, so that can be another one of my evaluations. And it's negative, so it's pointing to the left. Great. Makes sense. And from here, I can do the force exerted by field on Q at 10 centimeter is given by the E field at 10 centimeter and times Q. So again, same thing, minus 3 nanocoulombs times minus 2,000 newtons per coulomb, and I get, the minus minus goes away, plus 6.0 times 10 to the minus 6 newtons, and it's a force to the right. So I think I'm on the right track unless I've screwed up my numbers. Okay, still not done with the math part, right? I did the first part, and it says determine the kinetic energy of the particle when it passes the 60 volt equipotential line. So it started from 20 volts, it started from minus 20 volts and ended up at, or it ends up at the end, but we're just checking it at the 60 volt equipotential line. Okay, I could do this just mathematically. I could talk about it. I could also draw a diagram. Even though it doesn't tell me to draw a figure, I find it always best practices to lay out my thoughts in the form of a picture. What's happening to the energies? If I want to do an energy bar chart, well, in the beginning, it's a negative charge, let's do a different color, a negative charge at minus 20 volts has what kind of electric potential energy, positive or negative? Well, if we go back to this idea that we covered in class, which was the electric potential energy of a system is given by the charge multiplied by the V field value. So the charge is negative and the V field value is negative. The charge at minus 20 volt has negative electric potential energy. What about at 60 volts? A negative charge at positive 60 volts, that's where I ended up, has, well, if I follow this idea again, it'll have, oh, sorry, I did this wrong. Negative and negative gives me positive, right? A negative charge at minus 20 volts, if you do negative Q and negative V, you get a positive UQ. A negative charge at plus 60 volts has negative UQ. Again, I'm using this expression over here. Well, then what's happening to the UQ? It's going down. But we know energy is a conserved quantity, which means I can do some sort of accounting and keep track of it. And since there's no work being done on this system, since no external work is being done on this system, the system being the minus 3 nanocoulomb plus the field, therefore, energy is, what's the word? Energy is always conserved, so that's not what we're thinking about. I'm thinking about energy is constant, right? Energy conserved means you can always keep an accounting of energy, where it's going and stuff. Energy for a system is only constant if there's no energy flowing in or flowing out of the system. In this case, that seems to be what's happening, so I can say energy is constant, which means I can draw an energy bar chart now. In the beginning, there's positive UQ. I don't know, I'll give myself 3 bars of UQ in the beginning. And this is initial stuff. And all of this on the side is final stuff. At the end, I know there is some negative UQ. And I can kind of see that the negative number is bigger. You know what? I'll make this 2, and I'll make this 1, 2, 3, 4. Okay, this is my UQ final. Well, if it's constant, we should be able to balance the initial and the final, and there's no work in the middle, so that doesn't help. Well, where does all of that go? Well, initially, there was no kinetic energy. But at the end, since it was being pushed to the right by different amounts of forces, our graph tells us there's a lot of final velocity, which means there's a lot of final kinetic energy. How much? Well, I have 2 on the left, minus 6 over here, so I screwed myself over by drawing too many boxes. But 6, 7, 8. Anyway, there you go. So basically, what did I write? I wrote UQ initial plus this is 0, this is 0, equals to UQ final plus K final. There you go. That, and again, I could have written this just down if I explained it in words. I like explaining it with pictures. Okay. Then I can rearrange this and I can write K final is equal to UQ initial minus UQ final. Well, that lets me find the final kinetic energy of the charge. Well, what is the UQ initial? Well, I already wrote down an expression, right? UQ is given by the charge times the voltage or the potential value. So the charge times V at what value? Where did we start? We started at 0 centimeter, which is minus 20, and we end at 9, which is 60 at 0 centimeter minus Q, V at 9 centimeter. So that's minus 3 nanocoulombs, and I have minus 20 volts and minus 60 volts. So I get minus 3 nanocoulombs times, what's minus 20 minus 60? 80 minus 80 volts. And I get from here 3 nano times 80. It gives me 2.4 times 10 to the minus 7 joules. Still not that big, because I guess all the charges and everything are very small. That is my kinetic energy final. I'll take the box off of that. Oh, that was a lot of things. And we're still not done. What do we have left? We have evaluate your solution. Explain how you know whether your answer is reasonable or not. Well, we have 3 answers, right? We have an answer over here. We have an answer over here. We have an answer over here. Well, let's go remind ourselves what we wanted to do. These answers we already evaluated when we were talking about it, right? I got a negative E field. I expected a negative E field pointing to the left, giving me a positive force. Same argument for this one. And let's see what we can make for this. Instead of making one big evaluation at the end, I'm going to do something unorthodox. Because it is such a long problem, I'm going to space out my evaluations on the side. Evaluation. My evaluation is from my earlier, how do I spell earlier? E-A-R-L-I-E-R reasoning. I figured that the E field must point left. My math gives me a negative E field, which in this problem corresponds to left. Corresponds to left. Okay, that is part of my evaluation, but that wouldn't be enough just because this was a big problem. Let's do this one, eval. Well, there's no point making the same argument for this. what I can do is compare the two magnitudes. In this case, the particle is in a region where the potential changes quicker with delta x. Therefore, the E field should be stronger. Stronger meaning larger in magnitude. And we see it is larger in magnitude. So that makes sense. I could also add the force argument over here, but I feel like it's redundant. I could say I expected the force to be to the right, but I already kind of made that argument up here. If the E field is to the left and the particle is negatively charged, the force is to the right. What about this last one? Well, this last one, I could kind of make an argument for this whole case, eval. Since it is a negatively charged particle, going from a low potential value to a high potential value, going from a low potential value to a high potential value, we know the high electric potential, low electric, we know the electric potential energy must be decreasing, right? It's the opposite for negatively charged particles. Therefore, that energy shows up as kinetic energy. Since the charge is incredibly small in value and the delta V is a reasonable value, I expect my kinetic energy to be small. So basically you're multiplying a small charge with a normal number for change in potential. I expect my kinetic energy to be small, which it is. Alrighty. Okay, so that's 3 different unique evaluations corresponding to different parts of the problem. I think that should be enough. We did the evaluation, we did all of our math, blocked everything off, we did our sketch, and we did a lot of explanations right in the beginning over here. Yeah, that should be a 15 out of 15, unless I really hate your diagram, which I kind of hate my diagram over here. Look at this awful wiggly stuff. There, maybe better. Who knows? Okay, that's it. Bye-bye.